Okay, I'll cover the rest of assignment 4's topics, I think, which includes some of the Cascode stage and the differential amplifier. Before that, I'll cover some of the topics I think I said the last conference call. For example, how to do PMOS analysis and some other things based on the assignment. I'll just try to clarify. So I'm going to go like quickly today because I need to get to the differential amplifier. So I kind of prepared the slides, so I'm going to go quickly through it. So don't need to take any notes or anything. Obviously, I'll put the slides as well as the video, uploaded. So just try to pay attention, and I'll try to go through it quickly so that you don't have to, pay attention for a long time. Okay. So I think the first thing I wanted to talk a little bit about PMOS notation. It might confuse some of you to, solve problems of the PMOS. So I'm just going to quickly tell you one method, and if you're comfortable with something else, like actually myself, sometimes I prefer just writing the magnitude of everything instead of, so I treat it as almost like an NMOS, make the VDD as ground, and the gate to source convert everything into positive. But whatever you follow, make sure you are consistent with it. If you match them, then it's very easy to get confused. So for example, here what I've shown is if you have a PMOS and this is your VDD, so you can imagine, so if this is inactive region, so you have some current flowing through inactive region, then you essentially have two batteries here. Let's say this battery is V1 and this is V2. So your VSG, not GS, but SG, because this is your source now and that's your gate, right? So that's equal to V1 plus V2. That's sort of the imaginary voltage source you can imagine. And so this is just your threshold voltage. So in order to form the channel, you need to be at least a threshold voltage. Now the reason I'm written minus VTP is because VTP is a negative number. For example, I'll show an example later on for 0.18, for example, the VT for a PMOS is minus 0.45 volts. So because I've shown this as the positive, this as the negative, which is true, then minus 0.45 minus of that, this will be 0.45 voltages, right? So let me take a quick example. So if you write the current equation for this from the source to drain, like in NMOS, it's a drain to source. In this case, it will be source to drain. Then it's mu PCox over W over L. And this is VGS, which in this case is a negative voltage, right? From you're seeing, gate to source voltage here. So that's your gate, that's your source voltage here. So gate to source voltage is a negative voltage minus VTP, but VTP is a negative voltage, so that'll become positive. So let's say your gate voltage was 0.9 volts, VTP is minus 0.45, so this will be minus 0.9 plus 0.45 whole square, right? So it's like NMOS, but everything is negative here. So here's an example. So for example, in a 0.18 micron, the VTP is minus 0.45 volts, and that's your mu P Cox, and that's your W over L. And let's say this is the current you want from the drain to source when it is an active region. So you want to make sure the source to drain voltage is at least greater than V effective. If that's the condition, then the V effective is the same equation, 2 times the drain to source current, mu P Cox, W over L. Actually, this is here, it's source to drain, otherwise this will become a negative number, and you can't take a square root of that. So it's negative square root of this whole number. In this case, I've already calculated this is 170 millivolts or 0.17 volts, right? So basically this voltage source, so V1 is actually 0.45 volts and V2 is 0.17 volt, right? So in other words, VGS, or in this case, source to gate is minus VTP minus V effective, which is 0.45 plus 0.17, that's 0.62 volts. So basically these two voltage sources in series is 0.62 volts. Or if you write from gate to source, then it'll be the negative of that, minus 0.62 volt, okay? So whatever convention you follow, make sure you're consistent with it. And this is sort of a consistent, or this is really how it is. So that's why I'm showing this. But like as I said, a lot of times I just use magnitude, make things simpler, but you have to be consistent with it as well. Okay, so we just calculated, for example, this voltage source is 0.5 volts, this voltage source is 0.17 volts. So the other side of the problem is if the current was given and I was finding out ISD, or the source to drain current, if I'm given these two voltages and I need to find source drain, I can do the similar thing where ISD is mu p C aux over 2W over L VGS minus VTP. And you can see here VGS is minus 0.62 volts, VSG is plus 6.2 volts, minus VTP, and VTP is minus 0.45 volts. So it's minus of minus, that becomes plus here. This quantity becomes plus. And if you calculate it, you should get the same 10 microamp number, right? Okay, so I just wanted to quickly go through that. I just wanted to quickly clarify, I think in problem 3.5, unfortunately I hadn't solved it when I gave it to you. It might have confused some of you. So it was actually a source follower problem. So you had a source follower and given some bias here, and it was shown that you had a resistive load and what's the gain. Now what it didn't mention in the problem, and it is a sort of a ill-defined problem, is that if you just take a load resistance like this and connect it from here to ground, you need to know what the DC voltage is here, because there will be a DC current which is going to flow here. But in the problem, it's actually assumed that there is no DC current flowing through it. For that to happen, you need to put a voltage source like this, which is equal to this DC voltage here. So that's all I wanted to point out in this slide, okay? So basically, whenever you get a problem like this, if they shown RL and they haven't mentioned anything, just assume that the DC current flowing through that is 0. Okay. Oh, this is something I just wanted to, most of you probably have figured this out. But whenever we have a diode connected transistor, I have never mentioned if it is an active region or not. When you have a transistor connected, and I basically mentioned why, or sort of gave you the legacy reason why it's called a diode connected resistor, because it's from the BJT era. So in BJT, for example, if you did the same mirror, you kind of draw like that, and you take the base and collect it to the collector, and that's nothing but just a diode, right? That's just a diode, and that's your voltage out here. So obviously in MOS transistor, there's no such thing as a MOS diode, but it is from the BJT perspective, it's called a diode connected transistor. Now you see here that the VDS, for it to be inactive, or that is saturation, for that transistor to be in active region, you need the drain to source voltage greater than the V effective voltage, right? Which is VGS minus VT. Now you can see here, because the gate is connected to drain, VDS is actually VGS, and VGS is VT plus V effective, right? So this is VT plus V effective. So which means that the VDS is actually VT higher than V effective. So for example, let's say you calculated the V effective to be 100 millivolts and VT is 0.5 volts, 500 millivolts. So this will be 600 millivolts, which means that it's 500 millivolts higher than the V effective, which means that it's well into saturation. So whenever you have a current source like this connected to a diode connected transistor, you can forget about this transistor. This is always in saturation. So that's the other thing I wanted to mention. Okay. Do not multiply I bias with small signal impedance. When we find the small signal impedance of this, that's delta V out over delta I out, right? If you have a DC current flowing through it, which is I out, okay? Well, I think I have that. Let me show you the example. So I think in one of the problems we calculated, I think it was the first problem, 3.1, I think. where actually we had 80 microamps, 20 microamps, but I've just made both of them equal. So if you have 20 microamp flowing through this transistor and you have this size, I think this was for a 0.8 micron, I believe. We calculated RDS to be 666 kilo ohms, right? And the I out was 20 microamps. That doesn't mean that the V out is equal to 20 microamps times 660 kilo ohms. That will be 13.32 volts, right? So obviously you cannot fit that voltage here. And I think I mentioned that when I was talking about active load. What is the difference between active load and passive, which is like a resistive load? The beauty of these active loads is you can make the DC biasing independent of the AC impedance, right? So in this case, all it means is that delta V out will be equal to, I don't know if this is obstructing it, delta V out equals to delta I out times 660 kilo ohms, right? So I think I'm taking an example here. So let's say you had a voltage source right across this drain and source. Let's say you had a voltage source right across this, some VDS here. And if that voltage source changed by an amount of 0.5 volts, then the current flowing through it will change by 0.75 microamps, which is a very small current because your impedance is high, right? And that's why it looks like a current source, because as you're changing the voltage, the current doesn't change as much. So again, I just wanted to clarify that. Okay, I think we covered Cascode current mirror a little bit last time. I wanted to show you a little bit why this Cascode current mirror is requires a higher voltage compliance. In other words, we need a higher voltage for it to be Q2 for a Q2, Q1 to be active than the wide swing current mirror, which is one of the problems I had given. And I showed you a PMOS, and I promised you that I'll do a NMOS because that way it's not confusing, because you have two things happening at the same time. So in this problem, we showed that both, just write this here. So this was, I think, a 0.35 micrometer CMOS problem. So all the W over Ls were given to be 50 micron over 0.5 micron. And now if all of the sizes are the same, that means this 0.3 milliamp also flows at the output. All the VGSs are same, all the V effectives are same, assuming there is no lambda effect, which means that even if the drain to source voltages are different, the currents are assumed to be same. That's just a simplified assumption to make your life easy to calculate DC currents where it doesn't change much. But when you're obviously calculated AC impedance, you need to take care of them. So if you calculate the V effective for all four of them, use the equation 2ID over mu n Cox times W over L, then you get 177 millivolts for all of them, right? Now, so what is the minimum output voltage such that Q2, Q1 is active? Because only after that voltage it acts like a current source. Before that, it'll just look like a resistor, right? Because you're not higher than V effective. So if you look at the V out minimum, which is required here, it's the drain voltage, right? It's this drain voltage here. So it's this drain voltage here, let's call this VD1, plus this V effective 2, right? So you have two voltages stacked here. Now V effective 2 is under your control because this drain voltage is what you're varying, right? But this one is already set by this bias structure here. So if you write the KVL around this loop here, and that's what essentially I've done, you'll see that it's VDS1 plus V effective is what the minimum voltage you need. And VDS1 is nothing but VGS, it's basically VGS3. If I write, let me write it here. So VDS1 is equal to VGS3 plus VGS4 minus VGS2. That's VDS1, right? And like as you said, since all the W over Ls are same, the current flowing through all of them are same, all the VGS are same, that means two of these will cancel. So you have only one VGS, which is basically VT plus V effective, which is also the same. And then you get another extra V effective on the Q2 for it to be in active region, right? So the thing is that if you just look at it, these two transistors, forget about the biasing here. You should probably ask yourself, saying that why do I need this VTN? This is probably a waste, right? Because if you just look at these two transistors, if I bias it such a way that this voltage is actually the VDS1, or in this case I've written VD1 here, is set to the V effective, and then I just apply another V effective, then it should be in saturation, right? So I don't need a VTN plus to V effective. And we calculated V effective to be 177 millivolts. So we really should have both of them in saturation 2 times 177 millivolts, so roughly 400 millivolts, right? Whereas here it's 924 millivolts, which means that I need higher voltage. And a lot of times this is undesirable because usually you'll have something on the top, like for example, a differential amplifier or some circuit on the top, and you're just going to squeeze the headroom out of it because you have a limited supply. Let's say, for example, I give you one battery, that's only 1.5 volts, or if I put two batteries, it's 3 volts. You're taking away 1 volt out of that just for your current mirror to be compliant. That's a lot of voltages, right? So and that's where the wide swing current mirror comes into picture. And I'll go through them step by step to show you why, how we get more output swing, or how we are able to squeeze this minimum voltage required to keep the transistors in active region. Okay, so we take the same example again, but so what I'm saying is, okay, I take Q3, and let's say this was that 0.3 microamp. I push it into this Q3, generate this bias voltage, put that into the gate voltage of Q1, I'll generate I bias in this node. Now I want to improve the output impedance, right? Because this is a current source, I want to make that output impedance as close to infinity as possible. So I want to improve it, and we found out from the small signal that if I put a series transistor like this and put a fixed bias on this gate, then my output impedance improves from just being RDS1 to actually being GM2 times RDS2 times RDS1. So it basically improves by this quantity, which is a lot of times called the self gain. But then we found out that, oh, I just needed V effective to make it active. Now I need VTN plus 2 V effective. So instead of just putting 177 millivolt and having a current mirror, now I need 900 millivolts, roughly 900 millivolts to make it current mirror. So we're trying to improve that. So like as I said, if you just look at this, you'll say, oh, I just need this V out to be 2 V effective, 1 V effective for this, and then 1 V effective for Q2, then I should have both of them in saturation. So the question is, what is this gate voltage I need such that the Q1 is active? Or in other words, what is this gate voltage such that VDS1 is equal to V effective, right? So in other words, the VG2 needs to be at least the minimum VDS1 voltage, which is V effective across these two, right? Across the drain and source voltage, plus the gate and source voltage of this. So whatever voltage you're applying here needs to make sure that you have the gate to source voltage, this gate to source voltage here, VGS2, and then plus this drain to source voltage, which is V effective, to keep it in saturation, right? So V effective 1 plus VGS2. Now, how do we do that? You can simply, so this is one way to do it. So you create so what you do is you take the same current I in and push it into a transistor of the same size as Q2. So that'll give you VGS3. And again, we are assuming lambda effect is not here. The output impedance is infinite for DC calculations, which is pretty accurate. So this voltage here now will be VGS2. So you got VGS2. Now you need this extra voltage V effective 1, and that's where we put this resistor here. So we drop this I in into this resistor so that you generate this voltage VR equals to I in times R, and we want to make this equals to V effective, right? So we want to make this voltage VGS4 plus, this voltage is VGS4 plus I in R, and since all the sizes are the same, currents are the same, then the VGS4 is equal to VGS2. So we got the VGS2 term here, and we want to make I in R equals to V effective 1. So basically choose the R such that I in R equals to V effective 1. And I'll show that in the next example, right? If you do that, then that is equal to your VG2. So you join these two, then now you have a bias, and you don't need VTN plus 2 V effective, but just 2 V effectives, and your two transistors will be in saturation, and you'll get a really high impedance current mirror right now, right? So that's the principle behind the wide swing current mirror. Okay, so how do we do it? So basically what I did was I just combined these two circuits, right? I took the top circuit here and the bottom circuit, and if you look at it here, you'll see that, okay, this circuit here at this bottom circuit here, you already have this transistor, which is here. Q3 is nothing but Q4 with I in going in it. You already have I in going in it. So if I just put a series resistor at this node and then connect this node over here, then I'll have the same circuit, right? So that's what I've done here. So basically I said, okay, I in, this is I in going into Q3, that generates your VGS4 for generating I out here, which is equal to I in. You got that part. Now I wanted to generate VG2 here, and I already got VGS3. I put a series resistor here, so that's VR equals to I in times R. You generate that, and then you have that, right? Now, this will work as it is. Now, obviously, this doesn't look like your wide current swing mirror, which you did. The reason for that is, like as I said, we have been neglecting that the change of the current due to the different drain to source voltage is 0, but that's not true. You'll have it change. So, for example, here the VDS is actually VGS of this transistor, but here the VDS is equal to V effective. That means that these currents will actually not match. Okay, so in order to do that, you do the next step where to keep, so you want to keep the VDS3 equals to VDS1, and that's where you do this trick of actually pushing a transistor right in this here. So if you see over here, this is nothing but the same circuit I drew on the left hand side. It just has the added benefit that now this drain voltage over here, this drain voltage over here is equal to this drain voltage here. The reason for that is the gate voltage is the same here. And if it is the same size transistors, Q4 is same as Q2, and same current is flowing through that. That means the VGS will be same. This VGS will be same. That means the drain voltages will be same. That means the current will match more accurately than the one on the left-hand side. So that's really how the basic principle of your wide swing current mirror. So essentially, what you're trying to do is you're putting this R such that you just give enough VDS here for Q1 to be active, right? So Q1 is active, and then Q2, you just make sure that whatever circuit you have on top, that can go as low as 2V effective with respect to ground, and you get a really high output impedance current mirror. So that's really the principle of behind this. Okay, so is everyone kind of following? Some things may not be clear. I'm going, like as I said, really fast. You can kind of look back at the slide or go back. But if you absolutely don't understand anything, please go ahead and ask question. We can stop and clarify. Okay. All right. So I think I'm taking the same current mirror right now. I want to show you that it really does give you a higher swing current mirror. So I took the same current mirror where we didn't do a wide swing. We just cascaded two current mirrors on top of each other, and we saw that we need 0.942 volts for it to operate like a current mirror, right? So now we are doing this. So same 300 microamps. We choose the same sizes, everything, but now we attach that series resistor to bias it much tightly. So like as I said, choose R if you just want to give exactly V effective. Now, just wanted to say that this is for just the purpose of solving the problem. But typically when we are designing the circuit, we don't give exactly V effective. Usually we give at least a 50 millivolt to 100 millivolts on top of it. The reason for that is you have a lot of changes over temperature and processes, so you want to account for that. You don't want to keep it right at the knee. You want to be well in the high impedance region so that you get the full benefit of it. Otherwise, if there are some mismatches, you'll go into triode and then you'll lose your benefit. So this is just for solving for the purpose of solving this problem. So typically, for example, like I said, I would probably give even as high as 100 millivolts extra. So I would say instead of 177 millivolts by 300, I would do 277 by 300. So this won't be 590 ohms. It's probably close to like 1 kilo ohms. So that's how you choose the resistor. So you choose that resistor, you drop, you basically put that 590 ohms here, and then you'll basically get 177 millivolts here instead of 177 millivolts plus 450 millivolts, right? Which was basically a waste. So the VDS1 now, you write the same equation. It's, this VGS3, which is this node here, plus the IR voltage, that's your gate voltage here, minus VGS2 is what this drain to source voltage is. And if you calculate that, and like as you said, everything is matched. So both the VGS should be matched. So VDS1 is just the drop across the resistor, which we just calculated, and that's 177 millivolts because that's the way we chose it. So now if you choose the complete output minimum voltage required, it's essentially 2V effective, which is 354 millivolt instead of 954 millivolts. So you save 454 millivolts by doing this current mirror. And when we start doing the projects, we'll be using lots of current mirrors everywhere. And wherever we need Cascode, not a lot of places we may not need Cascode, we might just use a simple current mirror. But most places where we do Cascode, we'll use a current mirror like this. Okay. This is another way of doing that wide swing current mirror too. Like as I said, you basically have this Q1 here, Q1 stacked on Q2, and you can independently bias this gate source voltage, right? So we used a resistor here to bias it, but instead of that, you can actually bias it with another transistor and choose the W over L such that VGS5 is greater than VGS2 V effective. In other words, you basically apply V effective here. You can do that as well. And in fact, most of the time you'll see circuits using this. So if you're asking the question, okay, what's the difference between adding that resistor and this? Well, you can see two differences. This has the disadvantage of actually you requiring another branch. So you're basically having another I bias. Now it doesn't have to have I bias. You can make it lower than I bias and just make this transistor W over L ratio such that you get this voltage, but then it may not match properly. So you have that extra current, which means that extra power. But the advantage this one has is if you go back to this one, sometimes this current mirror here may not have enough headroom to allow this voltage drop here. Because you had VGS, now you have added this extra 177 millivolts here, or in some cases it could be 200, 300 millivolts here. Now this is VDD, let's say this was 1.8 volts, you eat away. So let's say this was also a cascode current mirror and you may not have that headroom. If you don't have that luxury, then you go with a structure like this. It's the same principle again, okay? Okay, just quick recap on the common source amplifier. And I think there was a question during the last lecture. Someone, I think it was Rudra or Karan, someone asked me, how do you solve cascode-based common source? Now, obviously, you don't want to take the entire circuit and draw the small signal. It will just become really complicated. So you should start looking circuits hierarchically. So if you've already solved some circuit and you know what the output impedance is and so on, try to use that as much as possible. So I'll kind of show an example here. So you've already done analysis for a simple common source amplifier where you have just one input device. So you just have one input device, and this is your current mirror, which is your active load basically, right? This is your active load. And if you look, so if I cut this node here and look towards the drain of Q2, well, I've said RO1 here. I should have written really RO2 here. That's your output impedance, RO1. And if you look into the drain of RO2, Q1, that's RO2. That's your output impedance. And if you draw the small signal, that's how it looks like. And I've neglected the body effect here just to keep it simple. And the gain here is just simply V out over VI. That's a small signal gain, is the transconductance of this device, Q1, GM1, times these two impedances in parallel. That is basically the impedance looking into this node from V out into your input device, and the other impedance is the impedance from V out looking into your active load, right? Now, you can make this thing as complicated as you can, but this principle remains still the same, because the output voltage that is generated here, small signal wise, will be whatever current you generate because of delta VI. So some delta VI you apply here, you get this current, but this current can't go anywhere, but it'll come out to the output, right? Because this is just one branch. If it comes out to the output, it gets dropped through these two resistors here, right? Two impedances here. So when you're so I've just shown that RO1 is RDS1. Well, this should be RDS2 parallel to RDS1, but you get the idea. That's just the impedance of the two transistors. One is the input device and one is the active load, right? Now, if you have a cascode, load, the principle still remains the same. You have this input device here, which is generating a current. So this current here, which is being generated because of this device, is GM1 times delta VI, some change in the current. And if you look at the impedance looking into Q3, this is a cascode current mirror now, right? And we already know the cascode current mirrors impedance, right? That's RO2 over here, which is RDS3 times GM3 times RDS4. It's the self gain of this device times the RDS3 of this. So it gives you that extra output impedance. And if you look into this node, it's the same thing. It's RDS2 times GM2 times RDS1, right? So you can simply use this. If you look at the previous one, if you just substitute these two numbers over here, your gain becomes, well, I didn't show it, but sorry. So from your previous gain, you knew that it was GM1 times RO1 parallel to RO2. It still remains the same, just that now it's GM1 times this whole quantity here, right? RDS2 times GM2 times RDS1 parallel with RDS3 times GM3 times RDS4. So basically that's your gain expression for a cascode. So you don't really need to do the entire small signal. I mean, you can do it just to verify this, and you should do it because that'll get you accustomed to how to analyze those cascode devices. But you can quickly analyze circuits like this, okay? All right, so I think that's all I wanted to recap from all the last lecture stuff. So I want to cover the last part of this assignment, which is the differential amplifier, okay? So differential amplifiers are sort of like, like current mirrors. You'll be using them pretty much everywhere in analog circuits. So it's very critical that you understand it. And we'll be doing a lot of differential amps. So as we go along, your concepts will be clearer and clearer. So I just wanted to touch the main idea of a differential amplifier and why you use it. So one of the main places we use differential amplifier is when we start designing op amps. The first stage here, this first stage over here, is a differential amplifier. If you remember your op amp circuits, you have this ideal block, right? And usually you have some input resistor, and you have a feedback resistor, RF, and this is usually your ground, and this is your VI and V out, right? So it has two inputs and one output in these op amps, and this two input goes into what's called a differential amplifier, differential transconductance stage. So you usually have a differential transconductance stage, and that goes into a high gain stage. So because if you remember your op amp circuits, you always assume that this gain, the gain of this op amp, is infinite, right? That's how you ideally calculate all your op amp circuit equation. So you assume that this current is equal to this because this is a virtual ground because this doesn't move. That's assuming that this gain is infinite. So when we are designing op amps, obviously we won't be designing with infinite, but it needs to be as high as possible. So that's why you have that gain stage, and then what you have is called an output buffer. And this buffer is actually, you've already done a circuit which does that. That's your source follower. So a source follower is a very simple buffer. And I think I mentioned it during the source follower. Essentially, it matches the impedance. So you have a really high output impedance driver, which you can drive because, you usually put this someone has to drive this RF here, which could be 1 kilo ohm, 100 ohms, 50 ohms, whatever it is. So you actually need a buffer which can provide the current. So you have a lot of voltage gain, but you cannot provide the current. So that's what this output buffer does. Takes a large input voltage and provides the current it needs to provide, because usually you have some load resistance here. And then you have a compensation circuit which compensates to keep it stable, and that's what we'll be covering once you've done your frequency response. That's where we'll start the two-stage op amp design. And then you have a bias circuit, which is all your current mirrors basically providing bias to this. So that's sort of where we use the differential. One of the main places we use differential, the amplifiers. Okay, so I'll quickly define some of the common terms we use in differential amplifier, and some of them you're probably used to it, but just so that I'm consistent with my notation and all that, we'll use this. So usually you'll have a differential amplifier where you have a positive input. I'm going to call it VIP. Sometimes we'll just call it VI plus or just V plus. And then you have the negative input here. So that's your negative input, and a lot of times, so we might call this VI plus or just simply V plus, and this one we might call it VI minus or just simply V minus, right? So you have two inputs and you have one output here. It doesn't necessarily have to be one output. You can have a differential input, differential output, but for this purpose, for the definitions of terms, we're saying that we have one output. So then we define the differential input, let's say VID, as the difference between the input to voltage. So it's VI plus minus VI minus. So it's whatever is the difference, right? And the common mode input we define as whatever is the voltage here, we add them up and divide by 2. So for example, let's say the DC voltage here was 3 volts, and well, let's say 1 volt. This was 1 volt. So if you take 1 volt plus 1 volt over 2, you just get 1 volt, right? So that's your what's called your common voltage, which means that that's a common voltage both for your positive as well for your negative, right? So we'll call that VCM. Then we define the differential gain. So because it's a differential input, it has two inputs. You can have a differential gain, which is what is the output for a given differential input. So what is your output voltage for a given differential input, which is defined on top here. And then you have the common mode gain, which is what is the output V out when you give a common mode input. In other words, when you move both the terminals in the same direction. That's your common mode input. Differential input is you're moving both the terminals in the opposite direction. And I'll show some graphical to make it more clear. I think most of you are familiar with it, but I'll show you that. Okay, so if you look at the output, then you can write it in terms of both the differential input and differential gain, common mode input and common mode gain, and that's how it will look like, right? So that's your differential input VID times this differential gain plus whatever common mode you have. So this is your VCM times the common mode gain you have for that circuit. So ideally, for a differential amp, what we want is we want this to be as high as possible. Like I said, you used to do your op amp assuming that it is infinity, and the common mode gain we wanted 0, right? We want the 0, and the reason for that, there are a couple of reasons. I'll just explain, maybe 2 of them. Okay, maybe in the next slide. So I just wanted to quickly show diagrammatically how it will look like. So if you have a differential amplifier, this is how your differential input will look like. Let's say you're giving an audio signal. So you start with a DC bias, and that DC bias is your common voltage. So let's say this was like, let's say 1 volt, and this peak is another 1 volt, let's say. So your positive input, let's say, has this sine wave, then the negative input has exactly the opposite sine wave on it. So if you write this, it's a complete time domain equation, then it'll look like this common voltage and then the sinusoidal. And the negative voltage will look like the same common mode voltage, but the negative of that same sinusoidal, right? So if you now write the VID as we defined before, it's these VIP minus this should be VIM. So VIP minus VIM. Since the VCMs are same on both, they'll cancel out, and this will become positive. So it'll get 2 times VD, and that's kind of understandable because this becomes your peak now differential, so which is 2 times VD times the same frequency sine omega t, right? And VICM is this VIP plus VIM over 2. If you add this to the differential voltage cancels out, right? Because it's a negative of that. Then you get 2 VCM divided by 2, then you just get VCM. So that's your common voltage. And this doesn't have to be, and I'll show you in the next slide, I've shown this as a constant voltage. That's how ideally you want it to be, but you could have some signal riding on this. So you could have some VCM sine omega, CMT, have some signal or noise, some riding on it. So you could have that riding on it. So just make sure that you understand this. So one of the reasons we want this differential input with common mode gain 0 is noise rejection. So for example, let's say you have this differential amplifier and you're giving an input which is Vs, let's say Vs over 2 sine omega st. That's your signal here. That's your signal frequency with this amplitude here. And obviously the negative part is exactly the opposite of that, minus Vs over 2 sine omega st. And your output should be whatever differential gain you have times Vs sine omega st, right? That's your differential input. This is what you should get. But if you, let's say you have some noise coupling, like let's say this is your VDD and you have some noise coupling. I'm just showing it sine omega t, but it's usually a wideband noise. You have all sorts of frequency in this. So you have some capacitance coupling into this node, then the VIP will have a noise riding in the same direction. It'll be plus Vn sine omega t, and on the negative side also will be plus Vn sine omega t, because they're added the same way, right? It's not added differentially because it's the same node which is connected to it. So your output, like as I said before, it's AD times the signal voltage plus ACM times the common mode voltage. But this is your noise voltage. This is your unwanted term, right? This you don't want. So you want this to be 0. But obviously this signal you don't have in control, but this gain you have in control. So you want to make, that's why you want to make this ACM as 0. So then whatever is coming out will be just your differential term, which is your desired. This is your desired term. So that's all you wanted. And this is your undesired term. And that's one of the reasons why you want that common mode gain to be 0. Okay, so how do we create a differential amplifier? Simplest way is you already know how to create a common source amplifier, right? So this is, I've taken two common source amplifiers, and I'm applying the positive voltage to one common source amplifier, negative voltage to one common source amplifier. So this will become your negative output because this is an inverting amplifier. So that's your negative output. This will become your positive output, and you have a differential amplifier. Obviously, in order to have single output, you need to take these two. So you need to have some sort of a block, and I'll show you what that block is in the end. You take that two negative, positive and negative, and you create V out over here. So differential to single-ended conversion. But that's at least your first stage. Now the problem with this is, if you look at the output, so you already know the gain of a common source amplifier is GM times actually RDS2 parallel with RD, but oh, sorry, I should write RD here. So this is really RD. This is RD here, but I've kind of approximated to RD because usually when you put this load resistance, it's a much smaller value compared to your output impedance, so it's just RD. But assume that whatever is the output impedance here. So, but for this purpose, it doesn't matter. This approximation should make a difference. So same way, the V out negative is equal to minus GM times RL times whatever is your positive input, right? So if you want to find out the differential gain, it's the difference of the output divided by the difference of the input. And if you just take this output and divide it, you should get GM times RL, right? So that's great. You get a good differential gain which you wanted, so that's desirable. But then the problem is, if you calculate the common mode gain, that's also GMRL. And like we said before, we want that to be 0, so that's undesirable. So we don't, this part we want to be 0. But obviously, with this structure, we cannot make 0, because if you make 0, then your differential gain also will become 0. The other thing I just wanted to quickly show is the sensitivity. So if you have a common mode gain, you have a sensitivity to that. And what I mean by that is, so I'll just quickly show in this graph here. So let's say you have some VICM, that's your DC voltage, whatever it is. Let's say you set it to 1 volt or something, and you give an input voltage, that's your positive. Your negative voltage is just an opposite of that. And you have a certain gain at the output. You have, let's say your output voltage common mode was also 1 volt, and it'll swing the opposite way as well. And if you take the difference of this, that's your differential voltage, right? And let's say this was your VDD. So this is your VDD. Let's say this is 1.8 volts. Now, as you saw from the previous slide, with the previous amplifier, if we change this common mode, now let's say I drop this common mode, because it's a negative gain, the output common mode will actually increase. So if I drop this input, this output will actually increase, right? So in the next slide, that's what I show. So if I drop this common mode here, the output will actually go up. The common mode output will actually go up, and the signal will start getting clipped because it can't go above VDD. So it will start clipping and you'll get distortion. So let's say, for example, this was an audio amplifier, and for some reason you have a large common mode voltage, then it's going to severely distort your output. So that's the other reason why you ideally want that common mode to be rejected, because that's not what we want to amplify. We want to amplify only the differential. Okay, so that's the basic differential amplifier, which I think you saw in one of the problems. Before I show you, actually, I'm not going to go into derivation of the common mode, the small signal gain. I'll just kind of intuitively show you how that gain comes into picture, and you can look into the text material. It's pretty easy to follow how it's coming. So I'll show you first the large signal behavior. I don't know if the text actually covered it, but first let me show you how this structure actually rejects the common mode, right? So here's a graph. I'm going to show this graph here. So what this is basically I'm going to show that even if you vary the common mode, well, before I go into the common mode, I just quickly, so if you have this bias current flowing here, and let's say this DC voltages are fixed, or the common mode voltage. So let's say this is 1 volt, this is 1 volt, just for argument's sake. then the currents will split halfway, right? So this drain current will be I bias over 2. This current is going to be I bias over 2. So you'll have exactly half and half current flowing through it. And that's what I'm showing in this slide over here. I'm showing that the drain current ID1 is I bias over 2, so is ID over 2. Now the common mode voltage, so let's say I vary this common mode voltage, add another volt or 0.5 volt, make this 1.5 volts and make this another 0.5 volts. The output current still remains the same. The reason for that is if the gate voltages are the same, the source voltages are same because they're the same node, right? So this is some Vs. So if the gate VG1 is equal to VG2 and Vs is same, that means VGS is equal to, VGS1 is equal to VGS2. If VGS1 equals to VGS2, and these are usually size the same, which means that the drain currents have to be the same. And for KCL to not get violated, if they have to be same, then they have to split half-half here, right? So that's why they remain same. So I can take the common mode, vary it as much as I want. Well, as long as I don't squish this current here, then it'll remain I bias over 2. And that's exactly what we want, right? Because then by the definition of the common mode gain, that common mode gain is 0 now. And that's exactly what we wanted. Okay, let's look at the differential large signal behavior right now, how it follows. So if you look at the differential, so let's say you apply, so it's 1 volt, and so you had, let's say, the DC 1 volt. Now I apply a minus, like let's say 0.1 volts here and plus 0.1 volts here, right? So this source voltage will still remain the same, right? The reason it will remain the same is because if it is anything different, the source voltage, well, it's the same node, right? So it has to remain the same. But my VGS here is 0.1 volt higher than this voltage over here, right? So this is 1 volt minus 0.1 volt minus point, so this will become 0.9 volts. And this will become 1.1 volt, which means that this VGS goes up by 0.1 volts, this VGS decreases by 0.1 volt. So this current is going to decrease. So instead of, so this will be some minus delta I here, and this current is going to increase, right? So if you follow this, let's say you follow the drain current of the first device here, ID1, that's this red curve here. At the middle, when the differential voltage is 0, then you have both the currents same, right? So you have both of them as I bias over 2. Then as the positive voltage increases, then the D1 also increases, but the same amount has to decrease. So whatever increases here, the same amount has to decrease here at this point, right? So at this point, for example, this even decreases more. So this has to decrease by the same amount because the total current needs to be I bias. This needs to be always I bias. And then as you keep increasing this voltage, differential voltage, all the current I bias is going to flow through the first transistor Q1 and it'll be 0 in Q2. And if you do the opposite, if you start making the VIP negative and VIM positive, then more current is going to flow into the second device, less current is going to flow into the different device. Now, this voltage here, over here, is roughly what? Is V effective, right? Because once that transistor gets more than V effective, the V effective than VGS, then it tries to shut off. Then it is just VT, then the channel is just barely on. So that's what, when we start dealing with linearity, we'll see how close we want this voltage to be before it starts distorting. Because as you get closer here, you'll start distorting. And this is very linear around this area. And for your op-amp, if you remember, if you have a really high gain, so let's say this is your negative node, sorry. So this is your negative node, this is your positive node. So whenever you have an op-amp circuit like that, if you really have a high gain, this voltage never really changes. So it means you're almost around this region. So which means that you'll be almost around the linear region. But you have to make sure that whatever input voltage you have here are much less than that V effective. Otherwise, you'll start distorting your amplifier. So now if you look at your differential, so let's say you take these two currents and subtract it, that's your differential current out, then it'll have this structure over here. So the current will be positive as your VID is positive, and it'll be negative, and it'll flip at when your input voltage is much less than V effective, roughly equal to V effective. And when we go into distortion, we'll look into how close you can come to V effective. So that's how the differential current works. So now in order to make it a voltage gain stage, all you want to do is take this current and just multiply with some load resistance or some R out, and you get a voltage. And that's essentially what this structure does, right? So basically you have a current flowing here in this, which is opposite of this current. You want to subtract that, and to subtract it, you want to take this current and actually push it here. And the best way to do that is actually put a current mirror, right? So that's your current mirror here. So this V out is basically ID1 minus ID2, or the other way around. That's your differential current. And the gain of this amplifier now, so if you look at the differential gain, it's GM1 times, because I'm just going to intuitively, running out of time here, I'll just intuitively show you here that if you take a differential voltage, let's say VID equals to some delta V, right? Like as I said, it'll be plus delta V over 2 here and minus delta V over 2 here, which means that since these devices are same, the current flowing through this will be minus GM times delta V over 2, and this will be plus GM times delta V over 2. So since GM1 equals to GM2, I can take either one of them, and so AD is equal to just GM1 times delta V. V out equals to GM1 times delta V input times this output impedance here. And the output impedance is, in this case, will be nothing but RDS4, because that's the impedance looking outside here in parallel with RDS2. Okay. Now, it's probably not obvious why this is RDS2, and if you do your small signal, you'll see it's RDS2, but I can give you a similar example, a small sort of a thought process to think why it's RDS2. So you know how you see your output impedance, right? So let's say if I just draw this stage here, and I'm going to just draw the other side. So you're trying to find out, so this is your Q2 here. So what you do is you apply a voltage source, some Vx, and you try to find out what the current is flowing through here, right? Now, for a common source amplifier, you know that this was grounded. So this was that output impedance, that Vx over Ix was simply RDS2. Now you might ask, like, I have a current source here. Why is it still looking RDS2? Shouldn't it be looking like a cascode? That is basically whatever is the R out of this current mirror times the self gain of this. You're correct, but this is a differential amplifier. What will happen is when you push delta X over here, minus delta X will flow here, such that this voltage node will actually not swing. So in other words, differentially, this will always look like a ground. And that's why you see RDS4. And that you should see when you do your small signal analysis. Okay. So, if it's not very clear, you can work it out yourself, and it'll become clear why that thing looks like common mode. For example, I said differential voltage, when you give a differential voltage, this is plus V by 2, this is minus V by 2, and this voltage doesn't change, which means if a voltage is not changing, a constant voltage is not changing, in small signal, it just looks like a ground, right? So when you're doing differential analysis, you can always make this ground, and all your small signal analysis will be fine. When you do differential, when you do common mode, this is no more ground. So for common mode, this impedance will appear and everything will look as it should. But for differential, you actually can ground that common node, and all your analysis should be fine. Okay. All right. I think that's all I wanted to cover. I'll just stop recording now, and can take questions if you have.